Welcome to the third season of That's So Second Millennium, the Catholic Science podcast where we explore the fascinating borderlands between science and theology through realms of philosophy, human experience, and more. Welcome back to That's So Second Millennium, episode 106. In this episode, Bill and I discuss statistics and p-values, and uncertainty in general in journalism and science. Hopefully that doesn't sound too dry. We've got lots of fun applications. Turns out journalism and science have more similarities than we realized before we started that conversation. As human endeavors, they're more alike than you might expect. So with that, here's our conversation. I was doing some, reading, and I actually still have a pertinent part of this one article that came out a few years ago about statistics and common abusive methodologies and statistics that have just grown more and more common over the decades, despite the fact that people who know anything about it know that this is really not the way to go. That's
fascinating.
Yeah,
because they have nothing else, right?
Exactly. That is your very pertinent observation. That we don't know what else to do. So you can't beat something with nothing, and it just sounds so plausible. It just sounds so nice.
Yeah.
So the thing that we're talking about is what's called a p-value.
Okay.
So a p-value comes up if you, let me see. This is one of the things where I'm like, in my career, I've sort of danced around it and I've encountered them, but I'm trying to think if I had to come up with a question like, when would you encounter one in the wild? I don't know. It depends on what part of the wild you're in, right?
Uh-huh.
As so many things do. So you could construct a p-value like, let's say you've got birds on two different islands in the Galapagos, and you're like, you're inspired by, Charles Darwin, and you're going to go out and measure the beak lengths of birds on these two different islands.
Okay.
So in that scenario, you're like, let's say there's something different about these two islands. It does not even matter what. Maybe this one island is older than the other one, and the volcano that created it has eroded down further, and the foliage is different, and blah, 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 blah. It doesn't matter. There are differences. Or maybe there are no differences, and you're still interested because the birds might be different.
Right.
So in this experiment, there's sort of an implicit, or there's an obvious choice of what's called a null hypothesis, which you've probably heard of.
Yes. Uh-huh.
So, what do you suspect the null hypothesis would be in this circumstance?
The null hypothesis is that there is no difference between the...
There is no difference. Yeah, in ordinary language, you'd say the birds' beaks are they're all about the same length,
right? Or
at least, and to get a little bit more formal about it, you'd say the populations of birds, these two populations have birds. Their beak lengths are, basically drawn from the same distribution.
Okay.
And then you come up with some measurement that you could actually make that would somehow allow you to test that. And you say, well, all right, so I will sample 200 birds from each island, and I will measure all their beak lengths. And then what I will do is I will construct I'll take the average, and then I'll assume some sort of statistical model, like maybe they're normally distributed with a nice bell curve like we know about.
Right.
And then I'll, of course, my actual 200 data points aren't exactly on a bell curve because that never actually happens. But maybe they're close, and maybe I can assume that the real population of like 20,000 birds on each island is really normally distributed or close.
Right.
And then I'll say, and then the mean is this far apart. And with enough statistical methods, I'll come up with a p-value. And the p-value could be something like, let's say it's 0.061.
Okay.
So it's like, or 6.1%, let us say.
Right.
So in the sort of contemporary abusive environment that we live in, as it grew in over the course of the 20th century, the crude technique that is widely decried and widely used is to say, well, at 0.05, results become significant. So what is the p-value actually telling you? The p-value is actually telling you that given your assumptions and the null hypothesis, so given the null hypothesis, the birds are really, their beaks are all about the same length. There's no actual difference between the two populations. Therefore, you'd expect the means to be the same of the whole population, and therefore my mean of my sample, which is my stand-in for the mean of the whole population, should be close to the same. And I'm assuming that they're normally distributed, and probably 2 or 6 other things that, we don't need to wade all the way through. Given all of that, there would only be a 6.1% chance that the means are this far apart. Let's say they're 4.2 millimeters apart on average, the beaks of those different lengths. And people say, well, it's not 5%, so it's not significant. But there's only a 6% chance that given all that other stuff, you would actually get these values to be this far apart, which is what the p-value does tell you. Right. Unfortunately, what people want to do is they want to turn around and say, because the p-value is, well, let's say maybe the p-value is 4.5% instead, maybe it's 0.045, and then all of a sudden you're good to go. There's not much difference between a 6.1% and a 4.5% p-value, but you've crossed that bright line.
Yeah.
And so what there's a strong, strong temptation to find whatever, crude or sophisticated method to hack the p-value so that it gets below that magic number. And you might be in a field with the magic number is something other than 0.05. 0.05 came about, if I recall correctly, because that's about 2 standard deviations away from the mean of the, if you have 2 things that are drawn from the same distribution, you would only expect about 5% of the time for them to be that far apart. Right. I lost the 2 standard deviation significance of that, but there you go. In any case, that's more or less the origin. It comes back from the 20s, and it was originally thrown together as something that was merely a pointer toward, well, now you should actually study it.
Yeah.
If you have something that's, around 0.05 or less, maybe it's actually worth studying. If it's 0.2, it's probably not important enough to worry about. But if it's 0.05, you should actually look at the problem. But the problem is you should actually look at the situation and see if there's something there. But instead, that's been taken as once I get to 0.05, there's something significant, and therefore I can publish, because by God, I need to publish because I need to make tenure.
Right.
Or I need a job. I'm a graduate student. I need a job. I'm a postdoc, and I need a next job. So, that's the whole. And so that's the background to some significant problems that we're facing, in the world at large. And I know you're more plugged into the news about, COVID and things, things like, face mask guidance changing, over time. And that sort of thing. And then there's a whole bunch of sort of methodological problems that, that's the problem. I was listening to a podcast where someone was commenting, well, the problem is that people are watching science happen in real time and they don't like it.
I like that. Yeah. That's right. Science is just as messy a business as the religion that science is supposed to be replacing in a lot of people's lives.
If not more so.
If not more so.
More so, yeah.
Yeah. Now, the place where I encountered statistics and their messiness first was, of course, way before COVID, and it was in election polling.
Oh, yeah.
And 2016 couldn't have been a better example of the messiness of statistics and all of the different things that are going on in the background of statistics. And I've had friends in the polling industry who kind of candidly say that polling has become simply less reliable, or at least less meaningful in some ways. I'm sure they found algorithms to improve upon this, but people no longer have landlines, so
Right.
many fewer people are receiving phone calls as kind of spam or junk phone calls.
Yeah.
And the more people are reached by cell phone, the more likelihood that those are more affluent people. So
There you
fewer.
go.
Yep. So there's all sorts of hidden things going on in the numbers. And of course, what you're saying is a kind of newsworthiness judgment. What
There you
you
go.
said would be the
The
equivalent.
journalism equivalent is newsworthiness.
Exactly.
Yeah, there you are.
So, in other words, why even report a survey if there's only 1 or 2 points difference between the two candidates? The only way that they could make that valuable is by looking to last week's poll, which had the candidates 6 points different, and then they can build a story that the lead has narrowed. But if candidates are only 2 points apart from each other, that's well within the usual margin of error.
Right.
So
at the margin of error that they admit to.
That they admit to, exactly, because those things we were talking about, like cell phones and all, those aren't even admitted to. Yeah, that's background stuff. Yeah. So statistics are really something. There's a reason why it's said that there's lies, damn lies, and statistics, but there is also very great truth in both journalism and science that we have nothing better.
Right? In so many cases,
Yeah.
Well, I mean, your alternatives are things like so there's a very specialized set of statistics that apply. I mean, many scientific fields have their own little specialized sets of statistics. So when I was at Notre Dame, solving crystal structures, if occasionally you'd have the opportunity to actually solve a crystal structure more than once in case you were worried about the quality of it. Not enough. I mean, unfortunately, doing it 20 times was really not on the table, but doing it twice was. And so you get to see that the software that you use to solve the crystal structure will, among other things, it'll give you what's called the unit cell. So the unit cell is a box that's basically the size of the repeating unit of the atoms inside the crystal. The lattice is made up of conceptually, it's made up these repeating boxes, and you could center the box anywhere. And then the atoms inside it are just replicated. You just slide the box over in all 3 dimensions. You build up the crystal conceptually that way, and it just repeats. That's called translational symmetry. That's the fundamental feature of crystals. All crystals have that. Even if they have no other kind of symmetry whatsoever, they all have to have that to be a crystal. So that unit cell is very important. The dimensions, the lengths, and the angles of the sides of the box, if it's not a perfectly rectangular box, are all very important to understanding, how the structure of the crystal is built. And so the software will give you its own sort of uncertainty on, it will give you, plus or minus 0.04 angstroms or something like that. And the size of a unit cell is generally going to be some handful of angstroms on each side. Might be 2 or 3 or 6 or 12 if it's sort of a biggish, complicated crystal. And then you'd solve the crystal structure again, and you'd be off by 0.2 of an angstrom instead of 0.04. So whatever uncertainty was in there, like it's clearly not replicable to that degree of certainty or anything close to it. Right. And so I never got far enough into it to understand, how are we getting this overly sure of ourselves? Exactly what are... I was focused on different aspects of the process rather than trying to improve that. But that's always stuck with me, that how did we get here? And
I love that.
It's not alone. It's not a solitary feature.
And it's so human nature to just not be bothered by the question, how did we get here? And to be so self-reflective, that you're actually asking yourself how we, did we take the right path? Did we take it far enough? Where is it leading us? Should we proceed or not? As you said, when there are grants involved, or when there are particular areas
you
of
shrug
interest.
and turn the crank and put the paper out, and go on to the next thing.
Yes, and of course that's very true in journalism, where the reporter has to write that story by the 6 p.m. deadline. So suddenly those statistics, they're not, he or she's not going to question those statistics. Let's churn out a story.
Yeah.
It's fascinating. It really is.
The assumptions underneath it just never bubble up to see the light of day.
Yeah. So how did you get interested now in? Well, you always were, and they always played a role in your scientific efforts. But was there something recent that drew your attention to the p-values and stuff like that?
Well, it's the whole. Well, I mean, part of it is that I started listening to another podcast, the Nature podcast, where this has been. I mean, the replication crisis. It has a name that people simply can't. That a bunch of studies have been put out over the years by people desperately seeking tenure or promotion or whatnot, and their graduate students and postdocs. That people have now dug into and started trying to replicate on a massive scale. And on a massive scale, they found out that things with a p-value of 0.05 are not necessarily replicable.
Oh my!
It could go again, and the reasons for that are they're all over the place. And of course, they dig into the weeds of the methodology, where the data came from. And they so seldom can be reduced to their own simple numbers. That's why the p-value is so attractive. It's a simple number. It's a grade. Just tell me what grade I got, right?
Yeah.
Like every student's rallying cry.
Yeah, that's another area where statistics are very shallow in their meaning.
Yeah. Mm-hmm. So it's But so I've been following that for a while, and I remember something that my master's thesis advisor, I remember her writing. Was it in an email that she was sending to someone that I was copied on, or was it something that I'd read in a grant of hers, a grant proposal? Well, she's very. So where she comes into it, and I've had her on the podcast, is the Ann Hoffmeister. She's 2 episodes back in the end of whenever that was it 2018 probably. And she's sort of a firebrand, controversial sort of figure, to the degree that she's not simply ignored, which is the fate of many of us. But in any case, so she's very concerned with heat flow and heat conduction. So I was actually reading a paper just yesterday or the day before that I saw linked on Twitter from someone, in the planetary science community. Very exciting paper about the internal structure of the moon and how long the moon had a magma ocean. Huh. As a geologist, it doesn't get much more exciting than magma ocean. I don't know how you feel about it, dear listener, but magma oceans are fun in planetary science. Like the entire, upper part of the mantle was a melt. This is so exciting. I can't explain how exciting this is. And all the chemistry that happens. That's why the moon is so beautiful, bright, and pale, is that you have this melt, and then what crystallizes out of the melt first sinks to the bottom, but what crystallizes out of the melt second or third is called feldspar. It's a very common class of minerals. It's what makes granite pale, is feldspar, and it floated to the top, and that's why the moon is its beautiful pale white, so much of its surface.
So much of it is feldspar?
Is the anorthositic highlands, a specific kind of feldspar. Anyway, but that's... So they were doing studies, and they were considering how long the moon could possibly stay in that state. And so they had pulled out, that there was an actual discussion, like she's winning. The whole point of this is my advisor, she's getting somewhere. She's getting to people finally. So I was looking at, someone has overestimated, there are all these estimates that were used for the thermal conductivity, because there's a whole big things change in a physical system when the heat is transmitted by conduction, which is just one end of something gets hot, therefore the other end of something gets hot.
Right.
As opposed to convection. So imagine you've got a spoon sitting in a pot of boiling water on the stove. So there's heat underneath the pot. The pot gets hot by conduction. So the heat just has to travel through the material of the pot, right? So the pot's not moving anywhere. But when it gets to the water at the bottom gets hot by conduction, because all heat, well, that's not true. There's radiation. That's how the bottom of the pot got hot, actually, is to a large degree radiation, although there's also conduction there. But the water at the bottom of the pot gets hot, and what happens to stuff when it gets hot? It expands.
It expands, right?
And therefore it rises, and the cold stuff at the top of the pot sinks to the bottom of the pot, and then it's its turn to get hot.
Right.
And so that sets up flow, and so that's convection. So it's an important question in any kind of, geologic, any place where there's melt, or any place where there's stuff that's so solid that it can, or that's so hot that it sort of can flow, even if it's not really liquid, if it's soft enough to flow. So that it depends critically on, well, can the heat travel by conduction? And if the thermal conductivity of something is high enough, it'll short circuit the whole convection process, and the material won't move. Is the material going to move? Or is the material not going to move? Really important question for understanding how a planet works.
That makes sense.
And so the old estimates were, Anne would say, made with faulty equipment and faulty assumptions, and they're all too high.
Okay.
And she's been studying it, and she's introduced equipment from the material science world, and has a better methodology for measuring it, and her numbers come out a lot lower. And so I was looking at this, and it was in one of these journals where things are only referenced by number.
Yeah.
So there's the author date reference system, and then there's just like numeric references to the end notes, to the sources that a scientific paper cites, and lots of other philosophy and other academic disciplines. So I had to go look at the end notes to be like, I wonder who was on that paper. Hoffmeister. Hot dog. She's getting somewhere. Good. And this nice, crunchy, high impact paper. It's like good for her. But it's, so I say all that to say, as she would say and was saying 20 years ago, we don't, like in geology, there just aren't enough person hours to go around. We don't replicate anything. Because we don't have enough people to do the problems the first time. So we're all out doing something, and what fun is it to replicate something? I mean, that's like, the kissing your sister version of science, right? I mean, somebody has to do it. You're contractually obligated to do it in order to say that you're doing real science. So, physicists and biologists have to go do this. But, in geology, we're too free and loose, and we're just swimming in problems that will never be enough of us to address all of them. So why bother with replication stuff?
Fascinating. Wow.
Yeah. But I mean, her comment was that, this stuff goes on in geology and no one even goes back to check, whereas in physics, there need to be 2 or 3 studies for us to start to believe that this is a real thing.
Gosh. So in a sense, it's a not a fake news problem, but an unexamined news problem. And I ask only
because not a lying news problem. We're not setting out
it's not
to
lying,
deceive
right?
Anyone.
Exactly.
Fake news is kind of generally.
Yeah, fake news is just another word for lying.
Intended to deceive. Yeah.
Yes, but there is a parallel in journalism. Where I've been told many times by editors, let's not write that story again. We wrote about that 6 months ago, or we wrote about that a year ago. And my thought is, well, A, something might have changed. B, a whole lot of people who read that don't remember it, and it's still a very important subject.
Yeah,
and other people they didn't read it to begin with, so now's the perfect time for them to learn it, and yet we don't have. Is it any wonder why so many people today are very dismissive of history? Because you're right, it's been learned. That was yesterday. Today is today. and I guess it's human nature first and foremost, but it's fascinating how journalism and science have these similarities.
Yeah, well, I mean, they're about information transfer between people.
Yes, yes.
And so there's bound to be similarities in their sociology, how they do business.
Yes, but I know that there's a book that was published just a couple of years ago by a professor from Catholic University of America. I believe it's called The Tyranny of Metrics. That takes it to a whole other area that we probably don't want to spend time discussing today, but it is a whole other big area, like how statistics are used in the business world.
Oh, yeah.
And how, they can deaden creativity. They are the measure of quality. And a lot of times they, like in things like employment reviews and those things, they look very good, very official, and very objective to grade somebody or something on the basis of 0 to 5.
Yeah.
But
they very effectively hide the whole panoply of assumptions and biases, to give that, that's certainly an aspect of it, around,
exactly.
Subjective, who put the metric together? How did they put it together?
Right.
What does it not measure?
What does it not measure is a great question that's never asked. That is very true. Seldom asked. And for instance, in the case of electoral polling, a lot of polls do not measure, is this person we've just called and inquired into, is he or she a likely voter? Is he or she even a registered voter?
Let alone is she a representative voter?
Exactly. Yeah, that hopefully is somehow being captured, but even that, because of those things like the income inequalities, who's more likely to answer a pollster's call and questions, all those things. Oh my goodness, it's a whole maze of different things that can lean toward uncertainty when statistics are presented to us as the most certain things on the earth.
Lies, damned lies, and statistics.
Exactly.
Yeah. Well, that's the thing. It's like it's easy to badmouth them, and it's so you think about the tyranny of metrics, and of course, that's true. But on the other hand, that's not like metrics exist for no reason. Right. I mean, because itself. I mean, without metrics, are we going to simply make decisions based on a pretty much raw, just projecting our biases and subjective impressions straight onto reality without even the intermediary of a metric?
and you're right. These days, that too is much too often tried as the answer. So,
I mean, that's endemic to humanity. That's
true too.
Nothing
that's
new
right.
about that. But yeah.
So you're right. It's good to have the statistics as a fallback position, it's even more than a fallback position.
And it's not. I of all people should not say it's all about. But one of the things, like I look at it as, and if reality wanted to tell me something different than what I already think, have I given it an opening?
Ooh, I like that. I like that.
It comes down to that to a large. I mean, that's why I like the in data science. I like the unsupervised methods more than I like the problem. I mean, of course, I'm also, potentially I'm just lazy, and with supervised methods, you have to supervise it somehow, and that takes work, right? Because I've got to come up. If I want to do a regression problem, then that means I need some training data set where I say if I throw x1, x2, x3, x4 in, I get y. Yeah. And I have to have a whole bundle of 400 or 500 cases. Well, ideally, I mean, to pick a number out of thin air, maybe 50, maybe 50,000 would be nice. And then I can build a model that says, okay, well, if you apply these 6 x's to something, then I should be able to spit out a y for you. And then I can actually see if it works out on the training data before I go herring forth into the wild before. And see if it actually works on anything else. Yeah. And then the classification data, if I have, if consumer Y well, okay, let's not do that. If consumer Bob has, metrics X1, X2, X3, X6, then he is a likely repeat buyer.
Okay.
I can classify him as yes, he is, or no, he is not. And then it could go back to a regression problem in terms of what is the probability that he will buy again from my website or something like that.
Right.
I don't want to mess with all that. I'd rather just do unsupervised, where I'm just saying, well, are there clusters? Are there bundles of people in, if you imagine in three-dimensional space, like, the temperature and the distance, the north-south distance and the east-west distance all, sort of cluster in one spot, so that cold things tend to be over here and hot things tend to be over here for some reason. I just like being able to find out, have the data tell me that.
Yes.
I don't know. Tell me, data. Is there any, bundling like that? Or, let the data tell me if they're all stretched out, in this one direction, 40 degrees east of north or something, and I didn't know that before I, let the data tell me.
Yes, yeah. Well, it's good that you're willing to inquire into data, in other words, to open the door to let reality tell you something. But scientists and everybody are always still at risk of not inquiring into exactly the right thing, or inquiring into the additional question that might give you either some valuable background to interpret the data, or might give you a completely different answer that, it turns out that the question you didn't gather statistics on actually makes the statistics that you gathered moot. I can imagine that happen. Are there cases in science where that happens? I mean, for instance, in the COVID situation, there's real disagreement on, those who are counting deaths as the primary measure. Some people would say that's the only measure to watch. Others would say no, the number of cases is more important, and the age groups are more important, and everything like that. So people aren't even sure that the statistics are being gathered on the right subjects.
Well, then there's that. Yeah, I mean, the scientist, the ideal is to gather all of the information, but of course that has a cost.
Yes,
Cost
and as you say, there's person
time.
power. Right. Yeah. There's time, there's cost power, person power. There's how much does the grant pay for?
Mm-hmm.
Right.
Oh, but the whole question of did we collect enough data? And it turns around and oh yeah, we didn't collect the right things. I mean, I face that all the time as a geologist.
Is that right?
Oh yeah. Yeah. That's easy to, So I mean, my project that I worked on when I was at Southern Illinois was trying to use data from the literature to come up with a model. And by the time I'd gone through the whole literature on this common class of minerals and vetted it down to all of the analyses where they'd actually collected the chemical data that I needed, I was left with 40 some analyses out of something. There are thousands of analyses in the literature of this mineral.
Oh my! Wow.
Yeah, because no one bothered doing fluorine and chlorine. Lord knows no one was doing, iron 2 versus iron 3. That's actually, that's hard. Fluorine's hard enough, but at least it's its own element, where its own line should be, even if it is difficult to get a good quantitation on it for reasons that go beyond the scope of this podcast. But
fair enough.
But yeah, that's always the case.
I think we're learning that just by dint of the conversation we're having, there should be nothing beyond the scope of this podcast, because everything is connected to everything else.
Everything is connected to everything. Unfortunately, we have finite intellects and finite time.
Oh, yes. And speaking of finite time, I guess we do have to be closing up. But I was probing earlier to see if part of your interest, your renewed or heightened interest in the p-values, are they were they especially accentuated by your boot camp studies in what I think of as or as informatics, but you had data science.
Yeah, I mean, some people use the term informatics, but I guess people think it sounds, I don't know, who can explain the fads in terminology? Like, who can explain why words, appear and disappear terms? Well, it comes up, in particular, the case that leaps immediately to mind is like, the situation I was describing earlier with regression. If you have a simple linear regression problem, a relatively simple linear regression problem, where you have, 3 or 4 variables that are inputs, and then you're looking for how an output variable changes. So one of your most important questions is, are there variables here that don't affect the output? Are there features, they're called? The input variables are often called features for God knows why. And then targets, I guess I get targets, kind of. I'm now so used to the terminology that it doesn't faze me as much as it used to. But when I first encountered, I like targets and features. What are you talking about? They're dependent and independent variables. Darn it! Why do we need all this different? I don't know. But there are 4 or 5 layers of this. Anyway, all that being said, endogenous and exogenous variables are my favorite.
Those are
who made those up?
Wow.
But the question is, maybe X5 doesn't affect Y at all. It doesn't affect Y at all. So if you conduct a reasonably, mildly complex linear regression analysis on, I know exactly the library, the stats models library would do this, and it spits out this beautiful. And you can do it in Microsoft Excel, and that's what I was doing for my Ansible work. But it will give you, a coefficient, the thing that you multiply it by, in order to get the answer that you want, and it will spit out a p-value.
Okay. And
that p-value should tell you, so let's be very careful here. Given your hypothesis, so the null hypothesis is that this variable actually does not affect the dependent variable.
Right.
That would be your logical or your sensible, your ordinary, what you would expect null hypothesis. And so the p-value is telling you the likelihood, if that is actually the case, for the points to be distributed the way that they are. So if it's obvious that for low values, I mean, if you've mathematically analyzed the data and it's in some sense obvious that at low values of X5, all other things being as equal as you can manage given your data set, the values of Y are low. And at high values of X5, again, everything else being as equal as you can manage, the values of Y are high, you will get a very low number for the p-value. Right. You can regularly get p-values that are like 1 times 10 to the negative 6th. So, 1/10,000th of 1%. Because it's just obvious from the data that these 2 variables are connected.
Okay.
Correlation is not causation.
Right. That's an important thing to remember.
We don't have time to go into that today. We don't necessarily know which direction the causal arrow points. I've been calling an independent variable. There's the assumption that it must be changeable and that the Y would then change in response, but it's not necessarily the case. Maybe the X's are just the things we can measure, and the Y is the thing that's hard to measure.
Exactly. Yes.
So, and that's a perfectly legitimate use of a regression technique. But yeah, so that's another case of the use of p-values that I have been had my face shoved in very recently and was reminded of, intrigued by. Well, but there's dozens of statistics you could measure besides the p-value.
I'm glad to hear that scientists are at least aware of these hidden potholes in analysis and use of statistics. Sometimes I'm afraid that at least the headline-seeking journalists really are barely even aware of statistics that the local lobbyist or PR person might hand them as proof positive of a particular platform or particular policy statement.
I don't know how many journalists, some. I don't know how many lobbyists, some, have ever tangled intellectually with the question of whether statistics are reliable or under what circumstances they can be trusted.
Yes. Yeah.
All of them.
Oh, exactly right. We don't have time to worry about that right now. We'll worry about that sometime in the future.
That's right.
Yeah, but this was fun. This was this is an area of crossover that I didn't even really think about in terms of our being a duo looking at these issues. I knew that science and philosophy and religion and all of those things had many crossover points. It's fun to have discussed this crossover point. Yeah.
I think so.
Yeah.
Well, hopefully you agree, dear listener, and we'll see you again in a few weeks. We'll bring you the rest of our conversation with Garrett. What's his first name again?
Oh, yeah. Dick Garrett is, Dick yes. Yeah. Talk about someone. Dick. Yeah. And he's a great user of statistics in an area where statistics are not particularly well used or understood a lot of times. Education.
Yeah. Well, we'll question a policy. Maybe we could bring that up next month. That would be a logical segue to what he was talking about.
Very good. And may I just ask, I just wish all of our readers that while you say that they're exciting, I personally hope that none of our listeners encounters a magma ocean in the next few weeks.
All of those things. That really would be a new chapter of Revelation. Some joke that I've heard this year, looking out the window to see what chapter of the book of Revelation we're on today. Here's, violence among the nations. Here's plague.
Exactly. Yes. Yeah. That's what fuels at least 1/4 of the Christian radio or TV station log time. Those questions. Yeah.
It is.
All right. Well, thank you for filling our podcast with interesting thoughts.
I hope so.
Yeah.
All right. Thanks, Bill.
Take care. Yeah. Thanks, Paul.
Thanks for listening to this episode of That's So Second Millennium. TSSM's audio producer is Morgan Burkhart. Our theme music, Igneous Grok, was composed and performed by Vin Marquardt. For my co-host Bill Schmidt, I'm Paul Giesting. Until next time.